Hi everyone, welcome back. Today we're going to be talking about geometric distributions. So, what is a geometric distribution? That's a probability model that is able to determine how many trials in an experiment it will take until one success has occurred, right? So, let's assume that each trial in the experiment is independent, so they don't affect one another. So this is similar to last time when we talked about binomial distribution, except binomial distribution, what that told us that time was what's the probability that we'll get a certain number of successes out of a certain number of trials. Whereas in this case, it's basically how many failures do we have to take, or not failures specifically, but how many trials would we have to go through in order to get a success. So here's the probability in the geometric distribution. It's expressed as probability of x is equal to q to the power of x times p, where x represents the number of trials that would be needed before a success. In this case, we don't have any combination here because the order does matter, right? This is the number of failures that would have to happen. Sorry, x is the number of failures that would have to happen. Q is the probability of one failure, and P is the probability of a success. So, for example, if a failure occurs 75% of the time, and I would like to know how many trials we would need before we get that success, right? How many failures do we need before we actually get a success? That's the probability of one failure, multiplied however many times, and then times probability of success as well, because that means the next one after all those failures would have to be a success for that to occur. Now, the expected value is going to be Q over P, and let's talk about why that is. Well, here we have the probability of a failure, and here we have the probability of a success. So if a success is more likely to happen than a failure, then odds are we're not going to have a lot of failures before we have a success, right? Let's say there's only a 25% chance of failure and a 75% chance of success. That means on average we'll only need a third of a trial, right? Which means that more times than not, we will end up with a success before any failures, right? This number is close to zero, which means more likely than not there won't be any, but there is a chance there'll be a failure or two before a success, but not likely. Whereas let's say that failures happen 99% of the time and a success only happens 1%, right? This is equal to 99. That means that on average before we get any success we'll have 99 failures and the last one will be a success. Or let's say it's 50-50, right? Well, then on average we'll need one failure before one success on the average time. Of course, sometimes we'll just get a success right away, and other times maybe there's two failures first, but on average it would be one, right? We would expect the number of trials before a success to occur to be one if it's, a fair thing, right? If it's flipping a coin, if it's 50-50. Now, that said, actually, that kind of relates and gets us into our next question over here. It says, in the repeated experiment of flipping a coin, what is the probability that the head occurs on the third flip, or that the first head occurs on the third flip? So in this case, we're searching for a head. We keep flipping our coin, flipping, flip, 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 until we get a head, right? And so in this case, a head is a success and a tails is a failure, okay? So what we need x to be equal to 2, right? We need x to be 2 because we need two tails or failures to occur before the third flip, right? Before the third flip, which is a success. Now, the probability of a success, right, of a heads is 0.5, and the probability of a failure is also 0.5, right? Both are 0.5. And so the question is, what's the probability that we get, the first heads occurs on the third flip? Or in other words, what's the probability that we'll end up with two failures? So two failures first and then a success. Well, let's see. P of x equals to 2 is going to equal 0.5 squared, right? And that's q squared because we're going to have a failure and then a second failure, and that's going to be times 0.5 again because of p is also 0.5 here, right? Because we then need a success to happen exactly on the third trial. So this is going to be equal to 0, 1.5 0.125, right? So in other words, it's not that likely, right? It's much more likely that we'll get it on the second try. The first heads will occur on the second one, or even the first one, right? There's a 50-50 chance that, the very first flip will be a heads and we'll get a success right away, right? So other scenarios are more likely than this scenario, in other words. Here they ask, what is the probability the first heads occurs on the sixth flip? So right off the bat, we know this is going to be a lower probability because that would mean that we'd have to get 5 tails in a row, which is not very likely at all. And then the next one, in addition to that, would have to be a heads, right? So for this one, we're going to do the probability that x equals to 5, that we need 5 failures before the sixth flip is a success. So that's going to be 0.5 to the power of 5, right? This is, and I should put in brackets, this is q5 times to the power of 5. And then this one is p, which is also 0.5. When the probabilities of the two, of the success and failure are different, it's easier to distinguish, but I wanted to put a note there that this 0.5, the first 0.5 is because Q is 0.5, right? The probability of failure is 0.5. And the second one is 0.5 because probability of success is also 0.5. So we could figure out that that's 0.0156, right? So that's the answer, 0.0156, and that's less than 2%. This is a very small percentage, but again, how likely do you think it is that we literally get 5 tails in a row, just on its own? That's pretty unlikely. And then on top of that, we're putting another requirement that the sixth flip must be a head. So that's a lot of requirements we're putting. And the more requirements that we put, the more specific that we make this, the more requirements we put, the less likely it is that all the requirements together are going to happen on average, right? Okay. C asks, what is the expected number of flips before you get ahead? Well, that's going to be Q over P, which is 0.5 over 0.5, which is 1. So, of course, sometimes, half the time we'll just get aheads right away, and it'll be 0 flips before getting ahead. Other times, there's also probability, though, that, there's also a decent chance that we won't, right? That maybe we'll get 1 or more tails first. And so, on average, we'll get 1 tail and then 1 head, right? That's the average of what would occur. Although, would that always occur? No, right? Not always, but on average, this is what would occur: is exactly one failure and then 1 success, right? All right, well, that's the first example done. Let's do 2 more examples. The second example says, what is the probability? Oh, sorry. A container holds 18 colored balls, 5 of which are gold, 6 red, and 7 are gray. A ball is chosen from the container and then replaced and repeated many times. So actually, we had this example with binomial distribution earlier, right? So this is the same example. They're just going to ask us questions related to the geometric distribution. And a reminder, something really important to note is that these are replaced and repeated many times, which means these are independent events, right? What just because we drew red this time doesn't mean we're more likely to or less likely to draw red the next time, because we're just taking something and we're plopping it back. We're taking one, we're putting it back. And so every time you reach into the set of colored balls, we have the same probabilities that we had previously. Okay, the first question asks, what is the probability that the red ball is for the first time on the second try? Okay, so I think what they mean is, what's the probability that, if we keep drawing our balls, that the first time we get a red one will be the second try? Well, that would imply that we'd have 1 failure first, and then we would have a success, right? So that we would first pull something that isn't a red, that isn't red, and then we'd pull something that is red. And x is going to be equal to 1 in this case, because we're going to get 1 failure before the second try is a success. Now, what's the probability of a success? Well, there's 18 balls, and 6 of them are red, so it's 1/3, which means that Q must be the other 2/3, right? So let's do this. What is the probability that x is equal to 1? Or in other words, what's the probability that we get 1 failure and then a success? Well, that's going to be 1/3 to the power of 1 or sorry, I guess I should put this in the right order. Not that it actually matters, but let's put it in the right order anyway. It's going to be 2/3 to the power of 1 times 1/3, which is equal to 2/9, 2/9. So in other words, it could happen, but not that likely a chance, right? There's just too many other possibilities that could happen. Okay, next one asks, what is the probability that the red ball is for the first time on the fifth try? So what does that mean? That means we have to have 4 non-red balls first, 4 failures first, right? So in this case, x is going to be equal to 4. The probabilities remain the same, right? Every time we draw a ball, there's a 1/3 chance that we could get a red ball and a 2/3 chance that we don't get a red ball. So what's the probability of x is equal to 4, right? 4 failures first would be 2/3 the power of 4 times 1/3, because then on the fifth try we get our first success. Well, that's going to be 0.066, right? Because in this case we had more specific requirements, and so that led to, a less likely probability for that to happen exactly that way. Good. Okay. The next one says, what is the expected number of times a ball is removed before you get a red ball for the first time? Well, let's see. That's going to be Q over P, which is 2/3 over 1/3, which is just 2, right? So the expected value would just be 2. Now, some people might say 0.67 over 0.33, which is about 2.03. However, that's going to result in rounding error, so I strongly recommend using fractions and not decimals when finding your expected values to avoid that kind of rounding error. And so this is another reason why we can see that getting the first ball in the second try is going to have a higher probability than getting the first red ball in the fifth try, because our expected value is for x to be 2. And x being 1 is closer to x being 2 than x being 4 is. So that also suggests to us that we're going to have a higher probability for A than for B, because we're closer to the expected value. And the closer we are to that average, that expected value, which that expected value is going to have the highest probability that there is for any specific value, the higher the probability is, the closer we are to that average value, to that expected value. Good. Okay, so let's do one last example. It says example 2, but this actually should say example 3, as this is actually our third example here. And it says a baseball player has a batting average, a 300 batting average, which is 0.300, sounds like. The first question asks, what is the probability that they get their first hit on their third at bat? So what this sounds like to me is the probability of one success is 0.3, right? 3 out of 10 times they get their bat, and the other 70% of the time, or 0.7, they do not. So that means Q would be 0.7. So 70% of the time they fail and they don't get a hit. 30% of the time they do get a hit. Now, I have no idea whether or not this is a good batting average or not. I'm not really sure. But either way, that's their batting average. And we want to know the probability they get their first hit on the third time that they go up to the bat. So that means they would have to have 2 failures first if it's their third try at the bat. So let's plug those numbers in, right? That means we would have 0.7, something with a 0.7% chance needs to happen twice first, and then we get our success, which happens 30% of the time, and that's going to be 0.147. Very good. Okay, then they're asking, what's the probability that they get their first hit on their fourth bat? Well, that would mean that they have to get 3 failures first, and then P and Q are the same as above. So let's put those in. And this is going to be 0.1, right? So this one is going to be less, right? They're less likely that that's going to happen. And then last but not least, what is the expected number of bats the batter needs to hit? Well, let's see. That's going to be Q over P, which is going to be 0.7 over 0.3, which is 7 over 3, which is 2.33, or 2 and a third. So about 2, I guess slightly more than 2 technically, but the most likely whole number we would have is 2. That said, do keep the expected value like this at 2.33. Okay, very important to keep it this way. So basically, on average, we would need to hit 2.33 times before we get that first hit. And so x being 2 is a bit closer than x is 3 to these, to the expected value, and that's why this probability is higher than this probability, right? Because our expected value of what we're going to end up with, which is going to give us our highest probability of all, is closer to 2. All right, well, that is it for geometric distributions today. Don't forget to complete the homework assignment on these, as these will be up on the test, that's for sure, along with everything else in this unit. Next time, we're going to talk about another type of distribution, which is hypergeometric distributions. So I will see everybody for that. Have a great rest of your day, and we'll see you next day for hypergeometric. Bye, everyone.